Okay, everyone, so it's time to begin now. And I just want to remind everybody that bonus work is due this Friday, chapters 1 and 2 pre-lectures and the bonus survey 1. So if you have any trouble getting on Lon Kappa or anything, please email me or the tech specialist, YT Yaktung. It's on the syllabus, his email. Actually, it's great to email us both, just CC one of us. So there's quite a lot of bonus work due, and I think you're going to really like it. It will really help you understand this stuff, and the bonus survey is a lot of fun. So today we're just going to finish up the stuff on part 1 on observational studies and experimental design. Now your first homework is due on Labor Day, and we're at the end of this class you'll have all the information to do this homework and this one, homework 1 and 2, which I'll open up. But I will have office hours, usual office hours on Labor Day if you want to come in and need help on Monday, so don't worry about that. And today there's office hours from 12:30 to 2. The TA will be there, and then I'll be there just for this week from 3:30 to 5. The usual office hours, you should really come in and check them out. The usual office hours, let's just check them out here. Here's our usual office hours. So today's Thursday, so it should be right here, 12:30 to 2 it will be, but in addition, I'm going to be there 3:30 to 5. So it's a nice space, so you're welcome to come if you have any questions. All right, any concerns before we start the class? It's a gorgeous day out, isn't it? I'll try to let you guys out early so we can enjoy this weather. It's amazing. Yes? Oh, her question is about iClickers. First off, we're not going to start iClickers until next week, so you have plenty of time. But her question is, if let's say someday your iClicker isn't working or something happens and you forget it, if you're in class, sure, you can write the questions down and show me at the end. Okay. Any other questions? Did you all get my email about that, about the iClicker points? Good. All right. So let's just start right now. And we'll go over to the document camera. And remember where we left off. We were talking about, so right now I'm on page 4 here. So everybody turn to page 4. And what we were talking about was why, this is not focused so well, hold on. Sometimes this helps if I go way in and then it focuses. It's giving you a headache, right? Wait a minute, it's supposed to focus if I do that. Oh well, did not do it this time. All right, so we're talking, yes, go ahead. Oh, good question. So her question is, did I post the notes as promised? Not yet. I'm going to post them at the end of this week. Okay, great question. Anybody else questions? Remember, interrupt anytime. Go ahead.
I had a friend who was actually interested in coming into this class and wanted to transfer in another staff class. They wanted to know if any better if there's room for the online course or if there's only room for the in-class course.
Yeah, it's a real problem. You think that, okay, his question is why isn't there room for the online class? It's online. Why don't you have more room? We should. That's stupid. We should have as much room because, you know, we don't need class space. So I've asked the department, I've asked to open up more online, but so far they haven't responded. So for those who want to get into the online and you're watching this and or if you're here and want to go into the online or your friends, tell them to, if possible, just register for one of the sections and you can treat it as an online class. As long as you come in and tell me that's what you want to do, then I can manually put you on Compass and manually put you on Lon Kappa, and you can act as if it's an online class. But if you're in the L1 class, you should really act like it's or in any of the in-person classes, you should act like it's an in-person class. Does that make sense?
Thank you. I'll come.
Okay, great. All right, time to start now. All right, so we were talking about how do we know if some treatment works or it doesn't work. We said that the best way to do it is we want the treatment and the control groups to be as alike as possible on all characteristics, even ones we don't know about. And we said the best way to do that is through a randomization. You can block first and then randomize. So that's what it says right here at the top of the page. Random assignment is key. As long as there's enough subjects, flipping a coin using a planned introduction of chance is the best way to decide who's in treatment and who's in control for two reasons. One, it eliminates human bias, right? You'll have accidental random bias, but that can go in either direction and will average out, all right? So with enough subjects, random differences average out. That is the key, all right? And then the other thing that we didn't talk about is that random controls are based on chance procedures. And without a chance process, we can't use stats to analyze whether the treatment really worked. We're going to be talking a lot about this when we do something called significance tests and p-values later on. So this is what they deal with if you've ever encountered them before. And I'll explain the basic idea, but we'll go into it later. So this is what significance tests and p-values, that you're going to hear about a lot, are concerned. And this is going to come up in we're going to look at it in part 6. I'm sure if you've had previous stats class or Stat 100 before, you've seen a lot of this. So what's the idea? So the idea is that, all right, so we want some way to, let's assume, we want to separate out what's due to chance variation, okay? Statistics is all about random variation. So, and we've tried to eliminate all the systematic bias, but then there's still random differences left. And if we use a systematic random procedure, just like flipping a coin to decide who's in treatment, who's in control, then we can measure that chance. All right, here's the idea. Let's say that the drug is a dud. It's no better than the placebo. So nobody gets really any treatment, right? And then if we're measuring, let's keep with our example of the SMART drug, right? So it's just a complete and utter dud. So at the end of the semester, what will I do? I take your overall scores, and let's say there's 300 people, and what I do is I'll put like your scores, imagine this, into write the scores on tickets and put those numbers, those 300 tickets, inside a box. And then I'll just shake the box up, just randomly shake it up, and then randomly divide it in two, to the treatment and the control. Now you know the treatment didn't work, it was a dud, right? I mean, all we're doing is a random division. And we're going to see, do you think that if we took the average of the treatment and the control, that we'd see exactly the same averages? Do you think you'd get exactly? There was no treatment, but just a random division is not going to give you exactly the same averages, is it? Because that's random chance. Just due to random chance, it's different tickets, right? So we can do that and measure, do that over and over and over again. And we can do we can see what the likely size of the difference between the two groups is just by the luck of the draw, okay? So let's say at the end of the experiment, there's a 2-point difference. Is that big or is that small? Like, let's say one class got a 90 and one group, let's say the treatment group got a 90% average, that's an A-, and let's say the other group got an 88%. It's only 2 points, but that's a B+. Could that just be due to the luck of the draw? How do you know? Well, what you do is you assume that the drug didn't work, that it was just due to a random chance. And then we can figure out the probability, just by the luck of the draw, of getting such a difference as 2 points, right? And that's what we're going to be doing. We're going to look at, the probability of that. And that's called the p-value. And if that is a very small probability, the likelihood would be very small to see that just by the luck of the draw, that wouldn't happen very much. They'd usually be closer together. Like if the sample sizes were really huge, that might be a big difference. And then we can call that, we look at that and we say, if the p-value is really small, if the chance of that happening just by random chance is so small, then we reject that and we think that it was due to the treatment. So that's the idea. We're going to be doing a lot of those significance tests. And so that's the idea of using probability to measure chance error, chance variation. And that's what statistics is all about. Okay? So if we didn't do a randomization and we did some other method, we wouldn't be able to figure out that chance, that it would have just happened just by the luck of the draw. Okay? So we're going to spend lots of time talking about that later on, but that's the idea. So now, people mentioned this last time about blind and double blind. You do randomization because you want the two groups to be as like as possible. But in keeping with that, if one group finds out they're in the treatment and the other group finds out they're in the control, then it's going to add a psychological difference between the two groups that we don't want. We want them to be exactly the same. So when possible, you would give the subjects a placebo, right? A fake treatment called a placebo. So this would eliminate subject bias, the psychological effect of knowing you're in the treatment group. We want to separate that out from the treatment itself. So we give the group the placebo, and then you don't know which group you're in. And the evaluator, it's double blind if the evaluator doesn't know either. So if I was really doing this experiment, what I would do is I wouldn't know who took the drug and who didn't. Because why? Because if I did, I'd probably be interested in the treatment, so I might pay more attention to the people who I knew took the drug, like ask them questions more, I might grade them differently. I would be biased. To eliminate that possibility, what you do is you have it blind. I wouldn't know until the results were all in, and after the study was finished, you would break the blind, and then I'd find out. So that's the idea of the absolute best experiment, is a randomized controlled double-blind study. Of course, with a lot of things, you can't blind the people. Like, even if you were randomly assigned to this in-person class or the online, you couldn't be blinded because you'd know whether you were sitting in class or at home, right? So you can't, and I would know. So there's no way to do a lot of experiments with the doing this way. But certainly you can do drugs this way. And all randomized controlled studies involving drugs are done this way. So that's the idea. And so now we did talk about smaller studies you should block first. It's always better to block first, but it's expensive and it's not so necessary in large studies. So you block first. Why? If you're really interested in some variables and you think they're relevant, you might want to make them exactly the same size. And even in big studies, medical trials, randomized trials, often block on things that they think are really important and could affect the results. And here's something else that's really important we talked about a little bit. Randomized experiments are ideal because they allow us to conclude causation, because we know that if everything is exactly the same or is as alike as possible between the two groups within chance variation, right, then at the end of the study, if there's a difference in their responses, since everything else was the same, the response must have triggered a chain of events that led to a different response. I mean, the treatment must be the cause because everything else was the same. It could have a long causal pathway, but it's the only thing that was different. So the treatment must have caused the response. Okay? Now, so that's really important. Now, many studies, as you know, like the one we're involved in right now, can't be randomized or aren't randomized, but we still want to get at causation. But the treatment and the control groups start off different. So we're going to try to, in the rest of that hour or hour and a half, we're going to look at ways that we can make the groups more alike so that we can get at causation, even in observational studies. Yes, question?
Are there a lot of conditions for you to conclude causation?
Say again?
There's a lot of conditions that you have to make sure about before you can conclude causation, right? Because
Oh.
requirements.
Before you, she asked, is there a lot of conditions, requirements that have to be satisfied before you can conclude causation? Well, the main condition is that the two groups are as alike as possible, right? You imagine yourself, like if you ever have to make a choice, you think, okay, I made this decision. How can you ever know if the decision you made was really caused some response? If you take some drug, is that really why I got better? Or you choose this online class, did I really learn better? The only way you could really get at that is to imagine yourself making the other choice. Sort of, it's called the counterfactual. To imagine yourself, that same self, making the other choice. Of course, we can't go back in time and do that. So the best way to do it is by making the two groups as alike as possible. And it's not perfect, but it's, is that what you were asking? Or were you asking whether you could extrapolate to other people? Like in all these studies that you read about, you wonder, okay, it worked for that group of people. Even if you do a randomized controlled double-blind study, it worked for that particular group. How can you extrapolate to another group of people? Maybe that's what you're asking too. I know. Oh, you're getting at something. What she's saying is, but I know every time we learn stats, we can't talk about causation. It's almost like a dirty word. I'm not joking. This has been this way for a long time, and it's finally, thank you, thank the whatever higher spirit. I'm so happy. Finally, the whole trend is turning because we all want to get at causation. And I was raised with that mantra, you can't conclude, it's correlation is not causation. They tell you that over and over and over again. But they never tell you what causation is. They just talk about correlation, and that's what we care about. So that's changing, and there's a whole branch of causal inference now that's really hot, and you're going to be hearing about in all your classes probably in the next few years. Then it's really changing, and there's some cool mathematical ways for us to get at causation. And that's what the very beginning of that we're doing in this class. And the arrows are important. So there's a lot of, so I'm really glad you're mentioning that because you're going to hear that, and I guarantee you it's going to be changing. That's going to be outdated, mark my words, you heard it here. Okay, so let's go. All right, so now we're going to go on to the next page in chapter 2. So, observational studies and confounders. So, this main problem with observational studies is that the treatment and the control group start off different to begin with. So things get mixed up. Once you see differences in their responses, how do you know if it's not the differences they started out with? So that's a big problem. Since the groups aren't balanced to begin with, it's difficult to conclude, but not impossible, causation. Okay? So if we suspect some differences besides the treatment are likely to be affecting the response, we can control for these confounders by breaking the population into groups where that confounder is the same. Eliminate that confounder and compare likes to likes. Okay? So this is the notice that I'm saying that observational study can show association, but it's hard to show causation. And of course we want to know causation because it means that we could change something, we could affect it. And everybody wants to change the world, right? Make it better. We don't want to just predict. If a doctor tells you you have a disease and you're going to die in 3 years or something, well, you want to know that maybe so you could plan and, arrange your life. But if he could give you a cause, then maybe you could do something about it to change it and prolong your life. So we all want causes, not just predictions. Okay, so the idea is that there's these possible confounders, right? Differences between the treatment and the control group. So the question is always, did the treatment, you see some association between the treatment and the response, and there's two possibilities. The treatment may have caused the response, like this. Did the treatment cause the response? You're seeing an association, why? And then what you'd be interested in is how or why it caused it. If you think that it caused it, well, how did it do that, right? So what this causal link, also called a mediator, if you're in, some classes, it's very commonly called a mediator as well. This causal link, and don't say causal. So many people say causal link. I got to change these glasses. See if I got another pair. So many people say causal link. It's not casual. There's nothing casual about it. It's causation. It's a causation link. Okay, don't get those. It's so easy to misread it. All right, it's causation. What this would do is, if the treatment really causes the response, you want to know how or why. So this explains how or why the treatment is causing the response. But remember, since the treatment and control groups started off different to begin with, one of those differences could be the real cause of the response, and that would be called a confounder. This is the simplest case of confounding right here, where there's a third variable, sometimes referred to as a lurking variable, you might have heard that, that's actually causing both the response and the treatment. So it's making it look like these two are causally related when they're not. They are associated, but the difference is, if it causes, if you got rid of this treatment, you get rid of the response. Whereas here, if it looks like this pattern, where it's just associated, and this lurking variable, this hidden variable, is causing both of them, well, this is just a marker for, if you get rid of this, you still have that arrow, it does nothing. So if you get rid of the treatment, you're still going to have the response here. All right, so these confounders, and don't call them a co-founder, that's what a lot of people seem to do. It's a confounder, that means to mix things up or confuse. So that's confounders, maybe, or confusers. Think of them that way. It's confusers, okay? What it is some difference, because we started off, this is all in observational studies. It's a difference between the treatment and the control that mixes up the results, that confuses our results, confuses in this case, it's going to make it look like the treatment, if you'll see them associated, and you're going to think that this might be causing that when it really isn't. Hold on one sec, I'll just finish that thought. causing response, I should say, to keep the language consistent, is causing the response when it's not. Okay, you had a question, someone?
Would it be considered like a cigarette study? They would be deciding what caused lung cancer, and you provide lighters in their pockets, maybe
Yes.
the lighter caused cancer.
Yeah, isn't that what we're going to do?
Oh my God, I learned in
We're going to, oh, you saw this before?
No, I learned in advertising, but I didn't know they didn't use the word.
Oh, okay. What did they use? They didn't. Okay, her question, she gave an example, a very good example of a confounder that we're going to get to in 2 pages. But it wasn't called a confounder, it was called, I'm just curious what they called it.
I don't think there was a word.
Okay.
I don't know if I remember it. That's why I didn't know if it was.
Yeah.
Students said they were confused.
In statistics, we haven't gotten the language straight, unfortunately, and that makes it confusing to students because you're going to see one term used in one class and one term used in another. And with confounders, that's really happened a lot. So I sympathize with you guys. In the back row, another question. Yes, go ahead.
I asked what it's more than one factor that causes the response.
Yes. This is one very clear-cut example that we're going to just look at, a very simple example, but there can be more than one confounder, there can be multiple causes, and there usually is. But I'm just trying to strip it down to the basic logic for now, to the simplest case. Okay? Good question. Any other questions? All right. So now let's just think about this. So I want you to remember that in randomized experiments, we don't really have confounders. Randomized experiments do not usually have confounders. And we're going to do simple cases in this course just to give the basics. So let's just say for this, you can get into complicated cases where they do, but let's just say randomized experiments do not have confounders. Why? Because the treatment and the control groups don't have these systematic differences. They're balanced to begin with. Systematic differences, bias. They still have random differences that we can measure with probability models. Sorry. Yeah, this isn't good. Okay. And again, this whole first week, chapters 1 and 2, I'm going to send you these filled in notes. Okay? So, yes, go ahead. Yes. If you have an observational study, you have to look for confounders before you have to eliminate them all before you can start talking about causation. All right. So now, what do we do? How do we control for these confounders? Well, statisticians adjust or control for these. What do? They want to get rid of these confounders. They want to compare, the treatment and the control group to be as like as possible. So what they do is they break the treatment and control group into smaller, more homogeneous groups along the confounding factor. Okay? So the confounding factor is the same within each of these subgroups, and then you look at the differences in responses between the treatment and the control group, and you see if that difference goes away, if the groups are balanced once you eliminate the confounder. Okay, and that's what we're going to be doing. This is called stratification, and it plays a similar role in observational studies as blocking does in randomized experiments. Remember? So like in randomized experiments, blocking is done when? At the start of before the randomization. Blocking is done at the start, at the beginning. And the key thing, it's before the groups are decided, before random assignment to treatment and control. Now, stratification is you're going to divide into subgroups, but it's done after people have, at the end of the observational study. Because the people themselves are choosing to be in groups. You have no control over that in observational studies. So you can't do it before. You're just looking, you're observing, and you say, okay, I want to make these groups more alike. So stratification is done after. This is the beginning, and this is after. Look how I spelled that. It's done after. An observational study. Okay, so that's the idea. Let's see. So we're going to go back to, what I like to do is use the same examples, the same numbers, and see how, what changes when under different circumstances. So now on the next page, we're going to go back to that same example that we looked at. This time is an observational study. So back in chapter 1, we had this blocking example right here where we blocked first into two homogeneous groups. We thought that prior grade was confounding, could be not confounding things, but was an extremely relevant characteristic, and we wanted to get that out of the picture and eliminate it, so to make it the groups balanced along those lines. So we blocked first, and then we randomly assigned. Now, suppose this is the real case that the students in this case, suppose the 36 students in Stat 200 were allowed to choose themselves instead of by random assignment to take the drug or not. Okay, so we end up getting these same results. Let's say 13 A students and 5 B students chose the drug. And the reverse here chose no drug. So let's just say so we get the same results here, right? Now, look at this. We've got completely unbalanced groups. We want to see whether the drug, how it affected their grades, right? But we've got like a predominantly A group here and a predominantly B group here, and that's going to mess up our results. It's going to confound it. If this group does better, how do we know that it was due to the drug? It's all mixed up with the fact that we've got different proportions of A students. It just could be because they're better students to begin with. How can we separate those two things out? So what we do right here is we stratify to eliminate the confounding effect of prior grades. So we compare A's to A's and B's to B's. Okay, now there's only 5 of these and 13 of these, but we're looking at the average overall grade of people who chose the drug, who are A students, to the average. So that's differences in numbers don't matter when we're looking at averages. Okay? I mean, of course, we're going to have a bigger random error here, but it's not going to, so this is the best we can do. Okay? And then we compare the B's to the B's. So, and then if the drug still looks like it's doing better, then it can't be the effect of more A students here because everybody has A's to A's. Do you understand that? So the stratification just means divide into subgroups along the confounding factor here. And we do it at the end because it's an observational study. All right? So that's the idea. We're doing this. Now what you can see that this is going to be a problem because let's say you also want to divide on other things. So when we stratify, our comparison groups are getting smaller and smaller, so there's more room for chance error, right? These 5, we only have 5 A students there. And what if we thought income was another confounder? Because high income students might be more likely to choose the drug and more likely to do well on exams, let's say. How would we stratify for both confounding factors? Well, look what would happen. What would we do? We'd have to break each of the 2 subgroups, each of these, like 13 A's in here. Here we can write it down here so as not to get confused. So let's look at the drug group. And we have 13 A's and 5 B's. And we're going to be comparing them to the no drug that has 5 A's and 13 B's, okay? So now if we wanted to divide them up into income groups, you can see like, okay, so we take the A's, so we divide them up into 3 groups. Let's say there is a high income, a middle income, and a low income. And we'll do the same here, etc. So there's a high, a middle, and a low. But look, we're going to end up with 1 student or 0 students in one of these groups. So you need a much bigger sample size. You're going to get, and we do the same with the B's. So the reason to do this is we'd want to be comparing likes to likes. So we'd want high-income A students who took the drug to high-income A students who didn't take the drug. But the problem is you need a much bigger sample size to do this with observational data than you do with experimental data because each time you stratify, the comparison groups get smaller and smaller and smaller. So that's a big problem. We'd have to do the same, with the B's, 3 groups and 3 groups. So that's the idea. And let's just jump right into a problem now. That's the one that this example that you've seen in another class. And I thought I made up that example. I really did. That's funny. All right. So, all right. So sometimes it's, yes, go ahead. You have a question? Oh, okay. So her question was, why couldn't at the end of an observational study, I think this is your question, why not at the end of this observational study randomly mix, are you saying mix these up and now randomly? Oh, you want to compare the same number of people. All right. No, you don't necessarily want to, you don't have to compare the same number in each group because we're looking at basically rates or averages, which means like a rate is per 100 or like the percent of people who passed or the percent of people who got 8. You see what I mean? Once with an average, it doesn't really matter whether you have different numbers here. Like if you look at a class average, you say, oh, the class average is such and such. It doesn't matter whether there's 500 people in the class or 100 people in the class. It's, right? So, good question. Yes, because we're not counting, it's not like more people is going to make them more A's. There's more A's, but we're not looking at that. We're looking at the percentage of people who wound up with A's at the end. Does that make sense? Or their overall average score. Yes, another question. Go ahead.
Wouldn't you get to a point though where the groups are so small that the averages couldn't be effective?
That's exactly right. That's the problem. He said, wouldn't you get to a point, and this is the exact problem with these observational studies, where these numbers are so small that the averages are subject to chance, a lot of chance variation. Like this one A kid might be completely different, not representative of other ones. Does that help? You only have a very small sample. And the smaller your sample, the bigger variation there's going to be. So it's a big problem. Did I answer your question? I forget who asked it, so I can't even see whether you're nodding or not. I hope, oh, you. Did I answer? Good. Another question in the back, yeah. What would be considered a big sample size? Excellent question. What would be considered? That depends on what effect you want to see. Your sample size, like if you want to see a big effect, then you can, you don't need, if you only care about seeing a big effect, you'll get it with even a small sample because it's a big signal, amidst all the noise, you're going to hear it. But if it's just a little signal you care about, like just, a tiny % difference, like just a one, then you're going to need a big sample to hear a little signal among a lot of noise. Does that picture help you? So, yeah. It depends on the size of the effect you want to see. Let's have a big effect you're going to just see with a small sample. A really big effect, like if the drug, there was a 20-point difference between the two drugs in your class and your averages at the end, we probably wouldn't even need statistics to tell us that. It would just jump out at us. Okay? Any other questions? Okay. And by the way, in this notebook, in the power section, we talk about how to calculate the sample size you need to achieve, to keep your errors down to a certain level and see the effect you want to see, as small an effect as you want to see. All right. So we are here. Now, here's this example again. And okay, so here's this crazy example, an extreme example that I hope you can, like the gal over there said she remembers, because it's a really, this is like a crazy example almost, but it's an iconic example that'll help you remember it. And that's this, that it's an extreme example. Suppose that observational studies show that people who carry lighters have a higher rate of lung cancer. All right? Now, you probably already know why they have a higher rate of lung cancer, right? But let's pretend you didn't. Okay? So you just see people who carry lighters have all this lung cancer. So there's two possibilities, that either lighters cause lung cancer, right? In which case we might want to know how or why, but then maybe lighters don't cause lung cancer. Maybe there's a difference between people who carry lighters and people who don't, since they chose themselves, and it's an observational study. And this difference is both causing the lung cancer and causing them to carry lighters. So let's look at this, and this is a classic. This is a very similar to the way your homework and certainly exams are going to be set up with these multiple choice questions, because on your exams, they're all multiple choice. So you're taking Scantron, so they're going to be set up. I'm not going to ask for long explanations. They're all similar to this. So so I think you should just treat this right now as we can treat it, think about it as if it was an exam question. And it says below are either possible confounders that would fit inside this mystery box here on the right, mixing up the result, making it look like lighters to blame when they're not. So something that's causing both lung cancer and people to carry lighters, okay? Or you're looking at each of these, are they causal links that it would explain how lighters are causing lung cancer? If they're causing it, how? That would be a causal link. It would fit right in here. Or there's another possibility, neither. There could be, we haven't talked about this yet, but there could be other causes of cancer, but ones that don't help explain why people with lighters are getting more cancer. in other words, the arrow's going towards the lung cancer, but it has nothing to do with the lighters. It's not causing people to get lighters. So it's not a confounder. The arrows have to be both ways because it has to explain the data that we're seeing that's connecting these two. So why don't we go through these, and you can lightly just think which one which for the first one, why don't I do the first one together with you? Okay, genetics. Some people are more genetically prone to lung cancer than others. I'd try it here first. Would genetics fit here? That would mean that lighters are causing you to be genetically different. That's crazy. So we can eliminate that one. Now we'll go over here. Does it make sense? We could just put it in here. Let's see, we could put genetics in here. Certainly you can be genetically prone to lung cancer. So that makes sense. But would you be genetically prone to buy a lighter? No. So this is not it. It's not a confounder, so it's neither. It's another cause of lung cancer, but it doesn't help explain why we're seeing this, so it's not a confounder. And that's really important to think about. So let's just remember, so this is option 1 here, where we're thinking about lighters cause cancer. This would be the picture. And this is option 2 here, where it's saying lighters do not cause cancer. Something else is mixing things up to make it look like they're causally related. They're associated. And why this is so important is because if lighters do cause cancer, we'd want to get rid of the lighters to reduce cancer. But if they don't, they're just associated in this way, getting rid of the lighters isn't going to do anything. All right, let's go to the next one. Age, let's do it the same way. Do they fit here? Does lighters cause people to get older? No, it's not that. Doesn't make sense. Then we put it here. I'll just put it down here. Age. Age, the older you are, the more likely you are to get lung cancer. That's for sure. So it does go this way. I don't need anything. It does go this way. But would age cause you to buy a lighter? Older? No. So again, it's not a confounder. It's neither. Now here's one. Smoking cigarettes. People who smoke cigarettes have a higher rate of lung cancer and are also more likely to carry lighters. So let's think about this. Do lighters cause people to smoke cigarettes? No, so it's not a causal link. Now, as you can see, smoking cigarettes both causes lung cancer and causes people to buy lighters. So there is the confounder. Does that make sense to everybody? Now, people are always asking me, well, are you bringing in outside knowledge? So this is just a logic exercise here. So I want you to just always pretend this is all you know, are the explanations given here. I know you can bring out outside information and things can change, but this is sort of just to get you the basic logic. So for all of these, answer assuming you only know what's said here. Okay? So now, so this is the confounder. A confounder. There could be other ones too. There's not just one. Now, lighter fluid. Perhaps inhaling the fumes from lighters can cause cancer via lung damage. Well, there, you see right here, this makes sense to go here. Lighters have fumes, so it's the lighter fluid fumes. So it's some chemical inside the lighter that's causing the lung cancer. So that is the causal link. And how about this last one? Why don't you do this last one on your own? What do you think to circle there? What do you think? You can just say it out loud. Neither, yes. Because again, radon is just another cause of lung cancer. It has nothing to do with lighters. Okay, So it's neither. So I think you've got the idea with this very clear-cut example that's really good to hold in your mind and remember when you're getting confused, because this is very clear-cut. Questions so far? Okay. So now how would we stratify? Now we suspect that smoking cigarettes is, what are we going to do to find out for sure whether it's a confounder? So what we're going to do, how can we determine whether it's the lighters or the smoking, or maybe some combination of both that's causing the lung cancer? So what we want to do is stratify, okay? So we are going to break the population into subgroups where the confounding factor is the same. This is called, we stratify to, this is a statistical, another use of the word control. Not only do you have control groups, but control just means adjust for. To control, you'll see that word a lot. It's different than, it's control for, it means to eliminate the influence of a possible confounder. The influence of the confounder on the response. Okay? So, what are we going to do? We're going to break the into subgroups where the confounding factor is the same. So, we're going to look at just people who don't smoke. Some of them might carry lighters for other reasons, and we're going to compare, there won't be as many lighters, we're going to compare just among people who don't smoke. We've eliminated smoking from the picture. Do those who carry lighters still have a higher rate of cancer than those who don't? And we're going to do that with the moderate smokers and the heavy smokers. Okay? So the picture, if you want to look at the picture, would be, okay, because it's an observational study, this is what you have to remember. In observational studies, we're going to have unbalanced groups to begin with. So we're starting off unbalanced. So what do we have? We have the treatment group and we have the control group. Just remember, these are the people who carry the lighters, and these are the people who don't have lighters. All right. But they're unbalanced to begin with on lung cancer rate here. They're going to be unbalanced. Why? On the response, which is, this is the response. That says response. I got to start writing nicer. And what we're measuring is your lung cancer rate. So they start off unbalanced. Why? Because not only do they have, it's not the treatment, it's mixed up with what? There's more smokers here. They have proportionately more smokers than they do here. And here they have less smokers. So they're not balanced. They have this is what it starts off with. So how can we separate out whether it's the smoking or the lighters? We can't, and that's why we stratify along the confounding factors. So these will be the non-smokers, and these are the results from the moderate smokers. This is really what happens, that once we control for smoking, these are the heavy smokers. Then the treatment and the control, the lighters and the no lighters, no lighters, there's no difference anymore in their responses. We're measuring the responses, and this is still the lung cancer rate. So this is the lung cancer rate. And as you can see, within each group, we've eliminated, it's clear that lighters don't do anything. This is the treatment is the lighters, and this is the no lighters. And now there's no difference, so lighters are not harmful. They're not harmful here, they're not harmful here. Here, but as you can see, these people are all getting more lung cancer because they smoke, right? It's smoking. You can see by this graph here, it's going up. The more they smoke, the more lung cancer they get. So, so in this case, since there's no difference here in this case, since the treatment and control show no difference in response, within each group, no difference in lung cancer rates within each group, we know that it's the confounder, which is smoking. The confounder is causing the response, which is cancer, an increase in the cancer rate, not the treatment, which is the lighters. So that's the idea of how it works, and this is a nice visual. In this case, it doesn't always work that way. You might see, we're going to see some cases where there's you could even, once you control for the confounder, you can even get things to switch the opposite direction, paradoxically. So that would mean that like lighters prevent cancer. Of course, they don't in this case, but we're going to see a case next where that happens. Okay, yes?
Still, I understand why. So when you have a lighter and you're saying more smokers, are you just like assuming that like lighters?
They have the proportions of smoke. If we think the reason why this is why we're seeing more lung cancer here, her question was she's not understanding how I know there's more smokers here and less smokers here. We don't know, but we assumed that people who smoke, people who carry lighters, this association here, we know this. It's something that we bring into it, that we know that there's probably this difference. Remember, all we're saying is that the two groups, when in observational data, the two groups are different. And here we're saying their distribution of the confounder is different here than here. Okay? Now, if people were randomly assigned to carry lighters or not carry lighters, then that would be kind of crazy. Then there wouldn't probably be any difference between the two groups. All right, so now a little preview right here. So there's really, there's two ways to control for a confounder. The first way is stratification, which you just saw. But we said the problem with that, one of the problems is you're going to have to have a big study because we're breaking things into smaller and smaller groups. There's another way that we can do that we're going to look at later, and that's by modeling. We're going to be including the confounder, what we think is a confounder, as a predictor variable, as an independent variable in a regression model. Including the confounder as an independent variable, that means a predictor, independent variable, in a regression model. And we're going to compare stratification. We're going to show how doing this is the same as stratification under certain conditions. And this is in chapter 28. So we're going to be coming back to this idea in regression, and that's the most common way people do it. You'll see in all sorts of studies we've controlled for all these variables, or sometimes call it another word, covariate. You put you put a variable that you think you want to control for, eliminate the effect of, inside your regression model as one of the predictors. And it will do a very similar thing. Okay, so that's to come. So we're going to go back to this. But now we're going to do some examples here. And I think we're going to skip some so we can get through this all. And also, so let's just skip it. It's fine. We're just going to skip this one. You don't have to do it. And let's just start with this one. All right. So sunscreen use in skin cancer. Observational studies have shown that people who use sunscreen have a higher rate of skin cancer. Does that mean that people should stop using sunscreen to lower the skin cancer risk? I mean, what we're asking is, does the sunscreen cause cancer, skin cancer? If so, how? Maybe there's some ingredient in there. Or, remember, it's an observational study, so we have to, this is like the treatment, and this is the response. Or is there some confounder? A difference between people who use sunscreen and people who don't, that's causing the skin cancer and causing people to use the sunscreen. Okay, so think of a difference between people who use sunscreen. Why do people use sunscreen? Because they're going out in the sun, right? Right? So the more people, so wouldn't that going at sun exposure certainly causes skin cancer? I already have some type of basal cell I used to be a lifeguard. I love the sun, so I have skin problems as a result. Sun exposure can lead to skin cancer for sure. And sun exposure is also causing me to put sunscreen over. Now that I know sunscreen, I wear it every day. So this is certainly a confounder. So if it's this way, well, think about it. You tell people that stop the sunscreen and you won't get cancer. Whereas it's this way, you don't tell them that. In fact, once you break into subgroups and look at people who just have heavy sun exposure, moderate and low, you find the scales tip the other way, that the sunscreen is not causing cancer, it's preventing cancer. They have people who use, within each subgroup, people who use sunscreen have less cancer, as long as they have the same sun exposure. Okay, so so that's the idea there. So what did we do to find this? How did we think of it? I thought of differences between the treatment group, if you can't come up with them on your own, the treatment group and the control group. I thought of what differences are there that both make them use sunscreen and could have cancer. And one of them is the treatment group, the ones who use sunscreen, as opposed to sunscreen. And these people have no sunscreen. And what would it be? I thought, oh, these people have more sun, more time in the sun. And these people have less time in the sun. There can be other confounders too. Okay? Now, do you understand this idea? Because I want to get on. I don't know if we have time. Do you want to try this one on your own, or do you think? We'll see how far we get, and we can go back to this. But I think you guys understand the idea. Okay? So we'll do this later. Skip for now. This is skip completely. This is skip for now, which means I'll try to get back to it. All right? And when I say skip for now, that means I'm going to post these notes when I post the notes. Okay? So if we don't get to it, you'll see the notes for this one. All right, now let's move on. All right. Now, Again, so the following are observational studies where cause and effect might be reversed. We're going to skip this one. We'll do skip for now. And we're just going to do the last one. I just want to show you that sometimes, yes?
The ones that we're skipping for now, like in the final, when you look through the notes, like.
Oh, good question. Skip for now, should these be filled in or not? Yeah, what we're going to, I'll try to limit the skips for now. So I do want you to fill in the skip for now later. So the question was, are you responsible for these? Yes, when I say skip for now. If I say skip, you're not responsible, okay? Does that make sense? And I will post those or else get back to them. So now the artificial sweeteners and the obesity. Basically, you'll see this a lot. I don't even understand why people aren't more careful, but it says a study showed that people who drank lots of diet soda, and I've seen this a lot, are more likely to be obese than people who don't drink diet soda, and conclude that artificial sweeteners may set up a craving for sugar that leads to weight gain. So they just assume that this is, okay, they're trying to do something surprising to get published. So they say, diet soda, even though you think the opposite, might have some ingredient in it or something in it that's actually causing obesity, because in observational studies, we see these two associated. And they do this so that so they can get headlines or something, because it's surprising. And they forget the more obvious reasoning, which you should also consider. What about, and there's some, because here they say because there's some ingredient that sets up artificial, you can see it because artificial, they're saying that that is the causal link. But they don't even consider that maybe the arrows, it's much more reasonable to think that the arrows would go in the other way. I mean, if you're overweight or obese, you want to go on a diet, and so you want less calories, so you're more likely to diet, and then you're going to have low-calorie food like diet soda. So just keep in mind that sometimes they have the horse before the cart. They have, the cart before the horse. They have things backwards, the causal arrows backwards. So this is just a reminder that this is a possibility, okay? All right, now to move on to some other things. All right, so here's this paradoxical result that's very similar to the sunscreen, where once you break into subgroups, the effect is reversed. So here's a study that looks like they looked at these women who smoked, and they found that the death rate, the overall death rate, this is an observational study. Let's just make really clear that that's what this is. So it's an observational study. So right away, you know you have to break into subgroups, and that this overall result could be confounded, because the overall result here shows what? It shows that smokers, right here, have a lower death rate than non-smokers. So does not smoking cause people to die more? Does smoking prolong your life? If so, I'd take up I used to smoke. I'd take it up right now. All my professors smoked in college. That's how I started. I was a philosophy major. They all smoked. And they'd be like, the whole time. Oh, that would be so relaxing. But I quit years ago. Still have a craving for it. Don't ever stop. Start. Well, you see, maybe I believe this study. I sort of want to, Oh, yes. Give me a cigarette, please. Okay, so, but we have to be careful. I know statistics better. So, can we trust that? No, because they chose themselves, right? So we have to break into like groups. So the question is, could not smoking, okay, not smoking, wishful thinking, right? Not smoking, I think there's a confounder. I think there's something that's causing people to die more and somehow not smoke. Now, what is that? It's hard to know. It's not an obvious one. What this study is is this is broken down into subgroups by age. And what you notice is how few older smokers there are. There's lots more. These are women, in British women way back when. It's a long time ago study when it was very unfashionable to smoke. So these women who are over 65, very few of them smoked because it was unladylike. You couldn't wear pants, you couldn't smoke. So the non-smokers are predominated by this older group here. Like, look how many there are. There's 193 here, right there. And there's only 49 smokers. So right here, you've got a lot of older people in the non-smoking group, and older people die more. So old age caused you to die, and in this case, old age caused you not to smoke. So this overall is misleading. You have to break into subgroups. Always break into subgroups if it's an observational study. Okay? So the overall results are misleading, and in this case, they're paradoxical because, as we know, smoking does cause you to die sooner. Not smoking helps you live longer, and you can see it right here. When you break it into subgroups, look at this. In every case, even though there's just a little difference here, the smokers die more. And here's what's really showing up in this middle-aged group. Here they're too young to die, to have the effect take in. Here, most of them die whether they smoke or not because they're like 100 years old. And here is where it's showing up. Okay? So this is called Simpson's paradox. And you're going to have an example in your homework of Simpson's paradox in which I used Bart and Lisa Simpson. So you'll recognize it as Simpson's paradox. It's one of my favorite examples. And you'll see it in your homework 2. It's the first problem in homework 2. And why it's a paradox is once the overall percentage is misleading because of the confounder, and once the confounder is controlled for by looking at subgroups separately, the overall effect is reversed. Same with the sunscreen. Sunscreen prevents cancer. The overall effect is reversed. All right, now our last example so this is for observational studies. Simpson paradox happens in observational studies. This is really important, where you always want to stratify. Observational studies you want to look at subgroups. Observational study, so you must stratify to get likes and likes. Now, we're going to look at something that looks the same, where you don't want to stratify because this is going to be a randomized study. And here, you do not want to break into groups at the end because you don't want to break the randomization. Okay? So what do you do with people who drop out of a study? This happens all the time in medical literature. They don't follow the program, they drop out, they don't complete the regimen. And people, what do you do with them? Well, you want to keep them in. Here, randomized study, compare everyone to everyone. You want to look at the overall results. Don't break into subgroups, you'll break the randomization. So compare everyone to everyone. Don't look at the subgroups. This happens all the time. What do you do with people who drop out of a study? Do you include them or not? Include them. Why? Here's a good example. All right. So so you have these people who adhere to the study. So you randomly divide people into two groups. This is a randomized controlled study. So these are randomly divided. It starts off great study, and then it can turn bad if you don't keep the original randomization. So you randomly divide into these two groups, clofibrate and placebo. And then you look at the overall results. This is what you should always do. And 20% died here and 21% died here, hardly any different. Okay? But what people do say, hey, not everyone took their medicine. If you look at just the subjects who faithfully took the clofibrate, like the medicine can't work if you don't take it, they say. So look at just these people. and compare, this is what they often do, 15% to the 25. Look, 15 to the 25. No, don't do that. Why? Don't make this comparison. No, no, no. Don't compare those two. That's what I'm saying there. No. Why? Because these are randomly divided. These are self-selected. This is self-selected. And there are going to be differences. The people who stick with the program, these are probably more responsible people who are watching their health in other ways, and that's why they're dying less. And these people might be slackers who don't take their medicine, they also don't exercise, don't eat well, and so forth. And you can see it with the placebo, the same difference. Here, you see the same difference in the placebo. Okay? So which comparison should be used? Adherers versus non-adherers? No. Everyone in treatment versus everyone in control. Now you might be asking, everyone versus everyone. 20% versus 21%. That's what should be used. Now, you might say, well, why don't we do this? Why can't we compare adherers in clofibra to adherers in the placebo, in these two? Why not? Because they have the same motives for adhering. The reason you can't is because often the drugs have side effects, and they don't have the same motive for adhering. Or often there's no placebo at all, like in an exercise. So you have to compare 20% to 21%, because in an exercise, you can't have placebo exercise, although that would be really cool, just somehow get exercise without doing anything. So, and here's an example where, on the next page, where this is made clear. Because this is something I really thought of doing, giving these really hard bonus problems. And I was worried about this, that if I gave really hard, even if I randomly assigned you guys to really hard bonus problems or the standard ones, randomize right here. If I randomly assigned you to these, I felt like what's going to happen? That a lot of people aren't going to do them. So what's going to happen is, if you compare adherers to in these two cases, you see that they have much higher, because you're going to get this. You'll probably get the smarter people here. The smartest people will keep doing those really hard bonus, and of course they're going to do well. It's not the bonus that's helping them. And here, this would be everyone or more people. So I was really afraid of, this happens all the time, that people have different motives for dropping out of one group than the other. So the overall, this is what I would decide on, and here it looks like sticking with standard bonus is better than trying to be all challenging because a lot of people won't do it. So this one is really keeping the original randomization. So in other words, you want, if you want to, it starts off a good experiment, keep it that way. Starts off a good experiment, don't ruin it by introducing bias, self-selection. And it's called intent to treat, and it's standard. Don't ruin it by, this happens all the time. It's really huge. It's very hard for people to understand, but I hope you got the gist of it here. Basically, it's called intent to treat analysis, and it's absolute standard practice in all medical and social experiments. And the reasoning is because if you start off randomized, don't mess it up, because then you can introduce self-selection bias. So keep to the original randomization, even if everybody doesn't follow the program. So that's it, and sorry I kept you the whole time, and come to office hours if you need help. And I'll post these notes completed.